Hello and welcome to the next video presentation by Mayer's Teaching Institute. Today we are going to be discussing about the atom and the first 20 elements that are important for school level study. In this, first we're going to start discussing about what are the contents of an atom. First of all, an atom is an indivisible part or the smallest part which is present within molecules and complex compounds. In an atom, which was initially thought as indivisible, was later found to have many subatomic parts or smaller parts within itself. The first being the electron, which is found to be negatively charged and is placed in the outer part of the atom, while the inner part consists of the proton and the neutron. The proton is positively charged, while the neutrons have no charge. This is important to understand that the neutron and the proton are in the center, while the electrons are outside. To maintain a perfect balance in the charge, the number of protons and the number of electrons are commonly the same. However, this can be different. The neutron number can be different. So with this, we've got two other terms coming into the picture. The atomic number. The atomic number is the number of proton or electron in an atom. As we said, that in an atom, the number of protons and electrons are always the same to maintain a sense of neutrality in their charge. Therefore, the atomic number is kept the same. You can either use it as electron number or proton number. Vice versa, the atomic mass number is the sum. I'm going to underline the word sum because I want you to understand it is the number of protons plus the number of neutrons. So this is important for us to continue further because atomic mass number is always fixed for a given atom. For example, hydrogen is found to have atomic mass number 1. Let that we have sodium, who's got atomic mass number 23. We've got chlorine, who's got atomic mass number 35.5. And we've got many of them as we will come through this video presentation. However, I would like to tell you all that knowing the first 20 elements from hydrogen to calcium, okay, is pivotal. It is pivotal. You should know. This is the first one. This is the 20th one. And I would like you to take charge and find out what are their atomic mass numbers given by the symbol A, atomic mass numbers. Find it out on Google. You'll always get them anywhere. Even though many a times in schools, they will give it to you all in the question paper while you are studying. I still insist that at least it is important that we should know the atomic mass numbers along with the atomic number of the first 20 elements at least in your life by heart. It is important to continue. At least, even if you want to have further understanding of certain concepts, certain basics need to be studied and mugged up. This is where you mug up, then the understanding comes in when we are going to be playing with the periodic table and other things. So continuing further, these are our first 20 elements, starting from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. We must know these elements by heart. And I've underlined the atomic number. It's kind of like a serial number order. It goes in the same line. The atomic number, the number of electrons or number of protons which is the atomic number, kind of gives you a sense of orderly arrangement in which you can remember the first 20 elements of this table. Okay. We will be discussing in my next video presentation about the periodic table. But however, it is important that before we move to the periodic table and understand the concepts that Dr. Henry Moseley had put into his periodic table, we should understand these concepts of the first 20 elements. Now, as we know that these 20 elements have this atomic number, which you have just seen as 1, 2, 3, 4, 5, 6, and so on till 20, we are going to do something known as the electronic configuration. In this table, I have kept for you the name of the element, the symbol of the element, and now we know the number of electrons in this line, the number of electrons. Now I want you to keep in mind that in the first shell, we can only have 2 electrons, then 8, and then by the 2n square rule, we go with 16, but we will be filling 8. And then again, opening another shell for 8, and so on. We will be continuing. If you see, they have already reached 20 elements, 20 electrons here in this line. Now, hydrogen has 1 electron, and therefore it has only 1 electron in its shell. Helium has 2 electrons, so it had 2 electrons in its first shell. But however, his first shell stomach is full, as a result of which it will move to the next stomach, and that is why when lithium comes, who has 3 electrons, the first 2 electrons will be filled in the first shell, and the latter will be filled in the next succeeding shells. So I will just cancel this out and show it to you all something like this. So we started with hydrogen, who had just 1 electron. Then we brought in helium. Helium had the second electron here. As lithium came in, the first 2 electrons were already sitting. It has a total of 3 electrons. So since the first 2 are already gone, it opens the next shell for the first. Successively, beryllium will also have 2, but now this shell, remember, can take up to 8 electrons, as a result of which, after beryllium, boron will get its third, carbon will get the fifth or the fourth electron in this shell, then the fifth, sixth, seventh, eighth, and on the 8th electron, we have finally reached neon. 2 on the inner shell and 8 on the outside make a total of 10, and that is why neon has 10, and the next second shell and the first shell both are filled. So we are just filling up the number of electrons successively like that. From sodium onwards, we will open up the third shell and go from 1 to 8. Once again, the stomach is filled at argon. We move to the next stomach, which comes the potassium, and the fourth shell starts filling. So it's like we're just pushing in the food, but the food has to open up in newer bags or little areas of your stomach, or newer stomachs, as we can say. And we are filling this food into the C, called the electron, the atom, and you are the nucleus in the middle, and that's your stomach going to be collecting all the food. Now, the electronic configuration, according to this table, I've only put the numbers. However, please keep in mind, electronic configurations are put in circular curved brackets. Okay, these circular brackets. If you do not put them in brackets, do not put the common, or school teachers tend to be a little this thing, that they don't appreciate the marking scheme when it comes to this. So when you're writing the electronic configuration for hydrogen, please put it in a bracket like this and say the electronic configuration is 1. Why am I going to do this? We're going to show this like how we put every shell now. Now look at every shell. There is only 2, so that comes 2. Here we've got 2 and 1, so you will put it like this: 2, 1, then 2, 2, 2, 3. Successively, all of them till 2, 8. When we come to sodium, there are 3 of them, so 2, 8, 1, and so on till we come down to argon at 2, 8, 8, potassium at 2, 8, 8, 1, and calcium at 2, 8, 8, 2. As we have split them up, you first took 2, you took 8, you took 8, you took 2, you took all into consideration, put them in the bracket separately, and this is called as the electronic configurational pattern of our atoms. Now I'm going to erase this also further, and we will be discussing about something known as the valence electrons. Okay, the valence electrons is another important concept for us to understand. The word or the meaning of the word valence electrons, I'm going to write it here. valence electrons. It is talking about the electrons in the outermost shell or the last shell. Now, if you talk for hydrogen, there is only one shell, that's the number one. So his number of valence electrons will be 1. Helium has only 2 electrons in the outermost shell, so his number of valence electrons will be 2. Similarly, lithium, if you see, the outermost shell is not shell number 1, but the shell number 2 becomes the outermost. So again starts with that number. It has only 1 electron in that shell. 2 electrons, 3 electron, 4, 5, 6, 7, 8. Coming back to sodium, the outermost shell becomes the third one because these become the inner ones. So therefore, the outermost is 1, and that's why it has only 1 electron, 2, 3, 4, 5, 6, 7, 8, and so on. The fourth is going to be for potassium and calcium. The fourth shell is going to be the outermost shell, while the others are going to be the inner shells. They have only 1 and 2 electrons successively in their shell. And therefore, as we take into consideration the concept of the number of valence electrons, the number of valence electrons in the outermost shell is what is called as the valence electrons. And these can always be a natural number from 1 to 8. And you have just seen it as we have been writing. They were only 1 to 8. But now we are coming to the next word called as valency. Valency. This is what I would say in a very common man's language. It's the marriage, or how many rings you are going to exchange when you are getting married between two atoms. Okay, therefore it is the number of exchangeable electrons, and I would say the reason I would say that it's the rings that are exchanged between two atoms, as an idea that the electrons are the rings that are being exchanged. So therefore, you can use this idea as a very common term, and therefore I would say that valency is a marriage between two atoms, particularly say a metal and a non-metal. Okay, now let's for simplicity's sake, let's say that the metal is the one who's given to give the electron, and the non-metal is the one who's going to take the electron. And as a consequence of which, there has been found that either some can decide, I don't want to exchange a ring, I want to be a bachelor or a spinster, I don't want to react, I don't want to get married, that's me as an atom. So they can avoid exchanging, and that's called zero. They're going to be the inert elements, the noble gas elements, the zero group elements, according to the terms that will come into the future. And up to 4 marriages are permitted. You'll exchange 1 ring, you'll exchange 2 rings, you'll exchange 3 rings, you'll exchange 4 rings, but up to 4. Okay. Now, when we have to do this, you have to take a little calculation for valency from the number of valence electrons. Okay. Now we see number of valence electrons. Some of them have 1, 2, 3, 4. In this case, electron, like let's take for example hydrogen, helium. We could have boron, carbon. Okay. Yeah. These are the valence number of valence electrons. I'm not talking about the I'm not talking about the atomic number. I'm talking about the number of valence electrons. Okay. I'm talking about this here. Okay. This is being spoken of. Now, hydrogen can either give 1 electron or take 1. So his valency is 1. However, we remember that when we drew helium, helium had 2 electrons in the first shell, and his stomach is full. He finds it more difficult to open up a new shell or to reduce down an electron from his existing shell. As a result, he decides that he or she wants to stay a bachelor or a spinster, and therefore does not want to participate in any reaction, and therefore remains inert in nature. However, in case of boron, they had 3 electrons in the outermost shell. Now, in order to fill this stomach, you need another 5 more. Okay, so let's say we are putting this, that this is the imaginary 5 more that we need to be bringing in, and there are already 3. But obviously, it's going to be difficult for boron to go and find for 5 partners to get electrons. And obviously, 5 is not the permitted number. So he decides that instead of me getting 5 electrons, I will give 3 electrons. And as a result of which, he gives 3 electrons. But then we have Mr. Carbon, who has 4 electrons in the outermost shell. Its atomic number is 6. So 2 in the innermost and 4 in the outermost. The 4 blues are supposedly could be taken electrons, sorry. Therefore, in 4, the valency is going to be 4. They can either take 4, they can either give 4. It reaches a midway junction. So like that, I've kept for you all an example here. This is our friend hydrogen, who's got atomic mass number 1 and atomic number 1. Electronic configuration in the bracket 1. Oh, sorry, I just turned the channel side here. Okay, so the number of valence electrons is also 1 in this case. The valency is 1 because, as I said, it can exchange 1. We spoke about helium atom. This is the helium atom. You can see very happily sitting with 2 electrons in its outermost shell, which is the first shell. Therefore, the number of valence electrons is 2 in this case. But however, because it's filled, the valency is 0. It does not want to react further. We've got another one who's lithium, who's got 3 electrons in total. It's got 2 in the first shell and 1 in the outermost shell. And as a result, the electronic configuration comes 2, 1. So the number of valence electrons in the outermost shell is 1. It can take 7 more in to fill the second shell, or it can give 1. So it finds it more of an easy duty to go and give that 1 electron rather than taking 7. For similarity, I've taken the sodium atom, 2, 8, 1. The first shell and the second shell are completely filled and therefore do not participate in any kind of interaction. But the outermost shell is most vulnerable to reactions, as a result of which the outermost shell can either take 7 or give 1. It becomes more easy to still give 1. I've also taken the example of calcium, who's got 2, 8, 8. 3 of them filled, the outermost having only 2 electrons. Here, the outermost 1 and this outermost 1. Now, either again take 6 to fill up to reach the 8, or you give those 2. And therefore, calcium decides that I should give the 2 electrons rather than collecting 6. So I've taken a similar example of oxygen. It's got 2 in the first shell and 6 in the outermost shell. Now, obviously, if it needs 8 to be filled, it's not going to search for 6 partners to give the electrons, the 6 electrons, but rather would say, let me get 2 more and become filled. And therefore, the valency in this case is 4. So what we would say is, if it is from 1 to 4, if there are 1 to 4 electrons in the outermost shell, or the valence electrons are 1 to 4, your valency will also remain from 1 to 4. Okay, 1 to 4. However, if there are more than 4, you will do 8 minus the number. So if there are 5 electrons, you will do 8 minus 5 and the valency will be 3. This is to give us the valency. Sorry. Let me just erase this. And we'll just put the valency here. And this is my number of valence electrons. So if I have 1, 2, 3, or 4 valence electrons, your valency will be either 1, 2, 3, 4. But if there are more than 4, you will do 8 minus the number. In a sense, if there are 6 electrons in the outermost shell, like in this case for oxygen, we do 8 minus 6, which gives us the answer 2. And therefore, this is how you're going to calculate the valency of an atom. So I've taken the liberty to pen this down for you, or put this on this presentation for the first 20 elements, the number of valence electrons and the valency. You can have a glance as you're going through this video presentation and look at how I've put it down. There's a certain trend. Okay, first one 1, 2, then we have 1, 2, 3, 4, 5, 6, 7, 8. Then again 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. That's for the number of valence electrons. But however, for valency, it goes 1, 0 because helium is filled at 0. There cannot be any more electrons taken in. Then we have lithium onwards 1, 2, 3, 4. Then because nitrogen has 5, it's 8 minus 5, so 3. 6 minus 5, so 2 for oxygen. 8 minus 7 for fluorine, giving us 1. 8 minus 8 for neon, giving me 0. Which I should come and take the liberty of telling you all that we've got in this very set 1, 2, 3, helium, neon, and argon, all three of which do not participate in reactions, and as a consequence of which they remain inert in nature. And with this is where I would end my video presentation. I hope you like this video presentation. Please do like, share, and subscribe to our channel. Your support will help us in making much more better presentations in the near future. Thank you so much.